Welcome back to the deep dive. We're looking at a huge shift in how we think about AI engineering this week. We're sort of moving past LLMs as just helpful code assistants and into the realm of fully autonomous, code engineers. Our mission today is to get into the paper, DeepCode, Open Agentic Coding, which really outlines a major leap forward here. The paper targets this thing they call high-fidelity document-to-code-based synthesis. What that really means for you is taking a massive source of information like a really dense scientific paper and turning it into a complete working software repository.
And that's always been the Achilles heel for these agents, even the best ones.
Right.
You have this massive information overload problem from the source document,
Right.
and it just runs headfirst into the model's biggest limitation.
It's memory, the context bottleneck.
Exactly, the finite memory. It's like trying to cook a 10-course meal, but you're only allowed to look at the recipe for one ingredient at a time.
You completely lose the big picture.
You lose the big picture, the agent just gets lost.
So DeepCode proposes a fix. They have a fully autonomous framework that reframes the whole thing as and this is their term, a channel optimization problem. Is channel optimization just a fancy academic way of saying they're aggressively managing the LLM's short-term memory?
That's a great way to put it, yes.
Yeah.
They treat that context window not as just a place to dump information, but as a critical, limited resource. So they have 4 key operations to maximize, the useful signals. They start with what they call source compression via blueprint distillation.
Okay, so a blueprint, like a summary.
Basically, yeah. It's like writing a killer executive summary of the paper first. A high-level map before a single line of code gets written.
And the second thing?
The second is structured indexing using stateful code memory. This just means the agent actively tracks the code it's already built so it remembers where everything is.
Right, so that solves the internal memory problem. But what about external knowledge? Stuff that wasn't in that initial blueprint, like a specific library it needs.
That's operations 3 and 4. For that, they use conditional knowledge injection via RAG, retrieval augmented generation.
RAG. We've talked about that before.
We have. And here it means the agent only pulls in those super specific external details at the exact moment it needs them. It keeps the working context clean. And then the final critical step, closed loop error correction. It runs the code, finds the bugs, and just fixes them over and over until it works.
Okay, that's the theory. Now for the moment of truth. The results. They tested DeepCode on the paper benchmark.
They did, and it didn't just do well. It achieved state-of-the-art results.
What does that mean in context? Who are they beating?
Well, the paper states DeepCode flat-out beat the leading commercial agents. We're talking big names here, like Cursor and Claude Code.
Really?
The architecture is just fundamentally more efficient for this kind of complex task than those more general tools.
But the truly headline-grabbing part, the claim that DeepCode was, and I'm quoting here, surpassing PhD-level human experts. I have to stop you there. That sounds like marketing copy. Is that a real reproducible finding?
It is, but you have to look at the specifics. The paper is very clear. The machine exceeded human performance on metrics like code correctness, the reproducibility of the results, and, how closely it stuck to the original scientific paper.
So not just writing code, but writing the right code.
Exactly. And if you connect that to the bigger picture, this isn't just about a better coding tool. This is maybe the first time an AI has shown it can audit and verify complex science without a human in the loop. It's a systemic change.
What an incredible advancement. So DeepCode solved that fundamental memory problem that held back all the previous agents. And by doing that, it achieved a kind of verifiable superhuman skill in turning abstract ideas into actual working code.
Right. And this raises a really important question for you to think about. If these autonomous agents can now accelerate research, truly accelerate it, by reproducing and verifying results just from reading a paper, what does that do to the sheer pace of future scientific progress?
Welcome back to the Deep Dive, where we take your stack of research and turn it into instant expertise.
Today, we're digging into a huge question.
A really big one. How good is AI, like right now, at doing real expert-level science?
And that's our whole mission today. Because, we're already seeing models like GPT-5 measurably speed up scientific workflows.
So it's already happening?
Oh, absolutely. We're talking about tasks that used to take human researchers days, maybe even weeks. Now they're getting done in hours. The acceleration is it's undeniable.
Okay, but if it's already that good, why do we need a new scorecard? It sounds like it's working.
Well, that's the thing. The old benchmark, GPQA, it's sort of broke.
Broke.
Yeah.
Yeah.
When it first came out, GPT-4 scored around 39%, a decent tough score. But fast forward just 2 years, and GPT 5.2 hits 92%.
92%. Wow.
Oh.
Okay, I see the problem.
Exactly. When a model scores that high, the test isn't measuring the frontier anymore. It's basically just a recall test. We needed a new metric, like yesterday.
And that's where this new paper comes in. This is our deep dive today. Frontier science.
Mm-hmm. It's the new standard, built to be genuinely difficult, original, and, well, meaningful. It tests expert reasoning across physics, chemistry, and biology.
What's so interesting to me is how they've split it up. It's not just one test.
Right. They have 2 completely different tracks to test 2 types of thinking. First, there's the Olympiad track.
Okay, what's that?
Think of it like a really, really hard textbook exam. It's 100 questions, short answer, constrained reasoning.
But then you have the other side of it, the research track.
And that's a whole new ballgame. It's 60 original multi-step problems, the kind of stuff a real PhD scientist might actually get stuck on in the lab. This is where it gets open-ended.
And the grading is different too, right? It's not just right or wrong.
Not at all. For that research track, they use a 10-point rubric. They're grading every single step of the reasoning.
So the AI has to show its work, basically.
Exactly. You have to score at least a 7 out of 10 to even be considered correct. It's judging the process, the logic, not just the final number. It has to produce something that would pass peer review.
So the results, this is the crucial part for you to hear. What did they find?
The gap. The gap is the whole story. The top model, GPT 5.2, showed this staggering difference.
Okay.
On that structured Olympiad track, it got a 77%. Really strong.
And Gemini 3 Pro was right there with it at 76%, right?
Yep, very comparable. But on the open-ended research track, GPT 5.2 scored just 25%.
Oh, wait, we all on 25%. After all that progress, it's failing research problems 3/4 of the time.
That's it. That's the headline. It's telling you the AI can ace the textbook exam, but when it gets into the lab with a new original problem, its success rate just plummets.
So what's breaking it? To get a number that low, something must be going fundamentally wrong.
Well, let's look at one of the problems. It involved analyzing mesonitrogen atoms in nickel-something silicyanine and its electronic structure.
Okay, that's a lot of jargon.
It is. Let's simplify. Basically, they asked the AI to predict how tweaking one tiny part of a really complex molecule would change everything about it. Its color, its function, its entire behavior.
That sounds like actual science.
It's genuine PhD-level prediction.
Yeah.
And the models just, they fell apart. They made calculation errors, logic errors. They fundamentally misunderstood niche scientific concepts, and sometimes just got the facts wrong on very specialized topics.
So the big picture here, the main takeaway.
It's that current AI is fantastic at supporting the structured parts of research. That 77% proves it. It's a powerful tool for accelerating what we already do. But there is a ton of work left to do on genuine, open-ended scientific thinking. That 25% score is proof that they still really struggle with nuance and original synthesis.
And we should probably mention the benchmark itself isn't perfect. It can't capture everything a scientist does.
For sure. It doesn't test for, say, generating a truly new hypothesis from scratch, or interacting with the real world, like analyzing video from an experiment.
Which leaves us with a final thought to chew on.
It does. If the most important benchmark for AI is the actual novel discoveries it helps us make, how do we even begin to design the next test? How do we measure creativity, not just complex problem solving?
Something for you to mull over. We'll see you on the next deep dive. Welcome back to the deep dive. Today we're getting into something that powers pretty much every big enterprise LLM out there. Retrieval Augmented Generation. RAG.
That's right.
We've got the abstract for a paper called CLaRa, Bridging Retrieval and Generation with Continuous Latent Reasoning. So our mission today, it's pretty simple. Figure out how this thing is supposed to make RAG better for you.
And it's a really ambitious paper. I mean, it's going right after the 2 biggest sort of foundational flaws in RAG today.
Right.
We all know RAG is great because it lets models look up new information, but as you probably noticed, it can get really bogged down.
Okay, let's dig into that pain point because I think it's key to understanding the solution here. The first problem, that's efficiency, right?
Yeah.
Just wading through mountains of documents.
Yeah, the long context problem.
But what about that second issue? The one that's a bit more subtle, the one that really messes with accuracy.
That's the disjoint retrieval generation optimization. Think of it this way. You have 2 different parts of the system. You have a retriever that finds documents and a generator that writes the answer.
Right. Two separate jobs.
Exactly. And during training, the retriever gets a good grade if it just finds a sort of relevant document, but the generator is only graded on the final answer.
So they're driving the same car, but they're looking at two totally different maps.
That's a perfect way to put it. The retriever can find something that's, vaguely related, pass that junk on, and then the generator is left trying to build a perfect answer for you out of flawed material.
They're not held accountable for the same goal.
Not at all, and that's where CLaRa comes in. It tries to unify them, to make it one single seamless process.
So how does it do that? The paper talks about continuous latent reasoning. What does it even mean for a model to go from searching text to operating in a shared continuous space?
Well, the huge shift is moving away from just searching for keywords or text chunks. Instead, it operates in the world of embeddings, these dense mathematical vectors that actually capture the meaning of the text.
Right. The meaning, not just the words.
Exactly. And in this continuous space, retrieval isn't really a search anymore. It's more of a prediction task. The model is actually predicting which latent vectors will lead to the best possible answer.
Ah, I see.
And that shift makes the whole pipeline much smoother mathematically, and this is the key. It lets you train the whole thing as one single unit.
Okay, so that right there sounds like it helps with the long context problem. If you can compress tons of documents into these smaller, meaning-packed vectors, you get way more efficient.
You do.
But how does CLaRa make sure that compression process doesn't just, throw out all the important details?
So they came up with this thing called SCP, a key-preserving data synthesis framework. It's not just summarization. They're actually supervising the compression using question answering tasks. So they're constantly checking, if I compress this document, can I still find the answers to the key questions inside it?
So it's a quality check baked right into the compression step. It guarantees those vectors are still, as they say, semantically rich and retrievable.
Precisely. The compression is useful, not destructive.
All right, now for the real game changer, getting retrieval and generation to work together. How do they get the part that finds the info and the part that writes the answer to share that same goal?
This is the core of it. CLaRa trains the re-ranker and the generator completely end-to-end, and it uses just a single language modeling loss.
Just one grade for the whole system.
One grade. The entire pipeline, from looking at the documents to picking the final word in the answer, is judged on one thing: the quality of that final output for you. If retrieval messes up, the whole system gets a bad grade.
That's brilliant.
Yeah.
But hang on, retrieval usually involves ranking documents, which is a very abrupt step-by-step thing. How does that final grade, the gradient, flow all the way back through the system so smoothly?
Yeah, that's the really clever technical bit. They use something called a differentiable top K estimator.
Yeah, what's that?
Normally, picking the top 5 or top 10 documents is a hard cutoff. It's like a wall. It blocks that optimization information from flowing backward. This estimator, it's like a soft bridge. It lets the training signal flow back through the selection process and all the way back to the retrieval parts.
I see. So it connects everything.
It completely aligns the goal of finding a relevant document directly with the goal of writing a good answer.
And the results seem to back it all up. The paper says CLaRa achieved state-of-the-art results on multiple QA benchmarks.
It did. And what's really telling is that CLaRa often beat the traditional models that were fine-tuned with normal text. It just proves that moving the whole process into this continuous latent space is just a better way to do it.
So the takeaway for you, the listener, is that CLaRa points to a future where these models can handle massive data sets much more reliably. It treats the whole RAG pipeline like one optimized assembly line.
It's the leap that could make RAG truly enterprise grade. It's moving from search to actual latent prediction.
And that leaves us with our final thought for you to chew on. If continuous latent reasoning can so drastically improve how LLMs learn from documents, what kinds of brand new, super complex, and previously unsearchable data sets could these systems master next? Think about things like scientific sensor data, or maybe even vast networks of symbolic logic. That's something for you to explore on your own. We'll see you next time on The Deep Dive.
All right, let's jump straight into probably the biggest problem for anyone using AI today.
Right.
Trust. I mean, you get this amazing articulate output, but how do you really know if it's true?
It's the constant challenge, yeah. These models are, incredible communicators, but they're also incredible, confabulators. Hallucinations, right. They just sound so certain even when they're completely making things up.
Okay, so for today's deep dive, we're going to unpack this using a fantastic source. It's a new benchmark called the FCTS Leaderboard.
Right, and our mission here is to really get into how they're measuring factuality. It's not simple.
And you can tell, I mean, the sheer scale of it. Aileen Chang and, what, 64 other authors?
Yeah, 64. It's a massive collaboration. And that just shows you how seriously the industry is taking this problem. What's really fascinating to me is that they get that factuality isn't just one thing, it's layered.
So it's not just a single test then?
No, not at all. The final score is actually an average of 4 different sub-leaderboards. Each one tests something unique to get a balanced view.
Okay, so let's walk through those 4 pillars. This is kind of your guide to how it all works. First up, we have FCTS Parametric.
Right. This one is all about the model's internal world knowledge. Think of it like a closed book exam, totally from memory.
So no looking things up, no search engine.
Exactly. It just uses its pre-trained parameters. It's a pure test of what it knows internally.
Okay, but wait. If the model's training data is, say, from 2023, isn't that internal memory already out of date? Why even test it?
But that's the whole point. You need that baseline. Because if its internal memory fails, then it has to know how to use external tools. And that brings us to the second pillar, FCTS search.
So that's when it gets to use a search engine.
Precisely. It evaluates how it does in, a normal information-seeking scenario. By separating them, you can figure out why it failed. Was it a bad memory? Or was it just bad at searching?
That separation is really powerful, yeah. Okay, so moving on from just text, we get to FCTS multimodal. This is where it gets really interesting, right? Because now we're talking about images.
Exactly. It's testing if the model can answer questions based on an image you give it. And that's a huge step. Factuality is no longer just about words. It's about, seeing and understanding the world visually.
And that brings us to the last one, the verification step. FCTS grounding, version 2. This feels like the big one, especially for those long, detailed answers.
Oh, it's absolutely crucial. This tests if the model's answer is fully supported by documents that you provide to it.
So it has to cite its sources.
Perfectly. And that V2 part is really important. It means they've significantly improved the automated judges that score the answers. Because, that used to be a weak link. Now the whole verification process is much more trustworthy.
So I think the big takeaway for you here is that factuality isn't just one simple thing anymore. This leaderboard gives us a much more nuanced view by breaking it down into internal memory, search, visual understanding, and verification.
It really does. It shows you the different parts of what we might call intelligence, and it leaves you with a really interesting question to think about. When an LLM gets something wrong, is it because it has a bad memory? Or is it because it's bad at checking its sources?
A failure of knowledge versus a failure of process.
Exactly. And what does that tell us about how we'll even define truth in AI going forward? Welcome back to the deep dive. So today we have a pretty clear mission. We're going to cut through all the hype and get into a really groundbreaking study. It answers what might be the ultimate security question. Can an AI agent out-hack a human professional? I mean, in a real, live enterprise environment. If you need that shortcut to being truly informed on this, this is the deep dive for you.
It is. The source we're looking at is an ArcZilla paper, and what's so important here, what's essential, is that this is really the first comprehensive evaluation of its kind. This didn't happen in some, sterile sandbox. This is on a massive university network.
And when you say massive, you mean it. The battlefield was huge. We're talking about a test scope of, approximately 8,000 hosts across 12 subnets.
That's right. And they pitted 10 experienced human pros against 6 existing AI agents, plus a brand new framework they built just to push the boundaries.
Right. And that new framework, that's the star player here, ARTEMIS. Okay, so before we get into the results, the dollars and cents, we need to know what's actually under the hood. I mean, if ARTEMIS is the AI that beat the best humans, what did the researchers actually build?
So ARTEMIS is designed as a really sophisticated multi-agent system. It uses dynamic prompt generation. It can deploy these specialized sub-agents for different tasks. And this is critical. It handles its own automatic vulnerability triaging.
Okay, so in plain terms, it's not just one AI. It's more like a self-managing team that validates its own findings before it even submits them. It basically removes the human oversight loop until way later.
You got it. And the results. They were just stunning. Let's cut straight to the core metric. ARTEMIS placed second overall in the entire competition and found 9 valid vulnerabilities, and it maintained an impressive 82% valid submission rate.
Second overall is big. But the key part,
The key part is that Artemis outperformed 9 out of the 10 human participants.
That is a staggering finding. Okay, but let's talk about the other AIs for a second. The older ones, based on models like Codex and Cyagent, they didn't do so well. They actually failed pretty badly. So did the researchers address whether Artemis's success was just down to its architecture, or maybe a testing setup that just happened to favor its design?
No, the study makes it pretty clear that next-generation architecture is the real differentiator. The older agents, they significantly underperformed most of the human participants. The success of Artemis.
Yeah.
It was all about these key technical advantages.
Okay, so what were those advantages? What did the AI agents leverage that humans couldn't?
They identified 3 main benefits. First, systematic enumeration, which just means, unlike a human who might get bored or rushed, the AI never skips a routine setup or scanning step.
Ever.
Right.
No shortcuts.
None. Second, parallel exploitation. It can test dozens of attack vectors at the exact same time. It completely eliminates that slow, one-at-a-time limitation of human work.
Okay, and the third advantage. I have a feeling this is the real game changer for the industry. Let's put this in CEO terms. You're telling me this one paper outlines a way to potentially slash penetration testing labor costs by, what, 70%?
That is the clear economic incentive, yeah.
Yeah.
They quantified the cost for some Artemis variants at just $18 per hour.
18.
18. Now, contrast that with the $60 an hour they costed out for the professional human penetration testers.
That cost difference is...
Yeah.
It's massive. But hold on. If these agents are still generating a ton of false positives, doesn't that cost advantage just get eaten up when a human has to go in and clean up the mess?
And that's the critical balance. You're right. We need to talk about that. AI agents do still have a higher false positive rate than humans. And critically, they really struggle with tasks that rely on a graphical user interface. Anything involving complex human-facing controls, that still requires a person.
So what does this all mean for you, our listener? I think the overall takeaway is that the technical gap it has closed. And AI, specifically Artemis, showed it could produce submission quality that was comparable to the absolute strongest human participants, at least in finding and validating these specific vulnerabilities.
And if we connect that to the bigger picture, it suggests, an immediate practical application here, boosting efficiency, reducing overhead. But those limitations we just mentioned, the false positives, the GUI problem, that means specialized human input is still absolutely crucial. You'll likely see humans managing and steering these powerful new agents, not being replaced by them entirely.
Which raises a really important question for you to consider. If this trend holds, the question isn't how fast the cybersecurity industry adapts its hiring models, it's how fast your specific role changes from being that solitary hunter to being a sophisticated manager of AI hunter teams, all driven by that undeniable $18 versus $60 an hour incentive. Something to think about. We'll catch you on the next deep dive. Okay, so today we are doing a deep dive into, well, the world of pure abstraction.
Right, because AI is now tackling highly complex theoretical mathematics.
And not just tackling it, but achieving a kind of conceptual mastery. But the real story here, the thing that caught my eye, is the efficiency.
Exactly. We're talking about an AI cracking PhD-level math problems, without needing a whole data center to do it.
So our focus today is on this new model, SeedProver 1.5.
And it's a formal theorem-proving model. It isn't just reading a theorem and spitting out an answer. It's mastering undergraduate and even PhD-level formal proofs.
Which means it promises superior performance while using a substantially smaller computational footprint.
That's the claim.
Wait, so we've solved difficult math and cut the energy bill. That sounds almost too good to be true. Okay, let's unpack this a bit.
Yeah.
How does it actually solve these deeply abstract problems with that kind of rigor?
Well, the key thing to understand is the difference between natural language and formal proving. LLMs, large language models, are great at natural language. They can write a proof that sounds totally logical to a person.
But it might not actually be correct.
It might not be. But formal proving, especially in a language like Lean, it demands absolute step-by-step rigor.
I've heard Lean is like an incredibly strict coding language, but for math.
That's a perfect way to put it. One misplaced comma, one tiny, faulty logical leap, and the whole proof it fails. It's totally unforgiving.
And that's what traditionally makes automating it so computationally brutal.
Exactly. So SeedProver 1.5 needed a completely different engine.
Which is where the reinforcement learning comes in.
Precisely. The core method is this large-scale agentic reinforcement learning, or RL.
So instead of just learning from a textbook of already solved proofs.
Right. The model is constantly accumulating experience. It does this by interacting with formal tools like Lean over and over again.
So it's like a math student playing millions of little abstract games.
That's it. And the goal is to complete the proof. But every single move it makes has to be formally, provably correct. That formal feedback loop is what dramatically boosts its capability and its efficiency.
I see. That distinction is huge. But hold on. If the training is that intense millions of these self-corrected games, doesn't the final proof generation part become a bottleneck?
And that's where the efficiency hack comes in.
The test time scaling workflow.
That's the critical bridge, yes. The TTS workflow is sort of the application layer. Because the model has this really robust internal experience from all that RL training, it can leverage new advances in natural language, proving to bridge the gap.
It translates our sort of human intuition into that rigid formal structure.
And with incredible speed.
Okay, here's where it gets really interesting for me. The proof is in the pudding, as they say, the results.
And they are pretty stunning.
Seed Prover 1.5 delivered superior performance, even with that smaller compute budget.
Yeah, take the undergraduate competition math. On the Putnam Bench dataset, it solves 88% of the problems.
88%. Wow, that's near mastery of some really difficult material.
And that mastery scales up. For graduate level stuff like the Fate H problems, it handles 80%.
And these are problems focused on verifying existing complex theorems, right?
That's right. But the big one, for me, is the PhD level, the Fate X benchmark.
Where it's not just solving knowns, it's discovering new mathematical lemmas.
And there, it solves a groundbreaking 33%. A third of top-tier frontier math problems. That's a massive breakthrough.
And there was a specific anecdote that really drives this home.
Oh, yeah. The Putnam competition. The sources say the system solved 11 out of 12 problems from the Putnam 2025 competition.
And the time it took?
Just 9 hours.
9 hours. That's,
Yeah.
well, it's an inhuman rate of conceptual processing.
It really is.
So, okay, what does this all mean? The big picture. The takeaway for me is that this combination of learning from experience and that high-quality, unforgiving formal feedback, it's a really powerful recipe.
I think it suggests we've hit a new inflection point in machine reasoning. This type of agentic RL, validated by formal feedback, holds just immense potential for the future of formal math.
And it makes you wonder, doesn't it? If an AI can achieve this level of mastery and speed today, what previously unsolvable problems in pure mathematics might it unlock tomorrow? Something for you to chew on until our next deep dive.
Welcome to the Deep Dive. Today, we're jumping into a brand new paper that just hit RGPT, and it details a really interesting piece of AI tech called 4D RGPT. Our mission for this deep dive is to get to the core of it, really.
Yeah.
We're looking at how AI is finally trying to gain what you could call true 4D perception in videos.
Yeah.
So not just what's happening, but where things are and how they're moving in 3D space over time.
And that's the perfect context to start with because, if you look at these big multimodal LLMs, they're brilliant with text and static images, just brilliant.
Yeah.
But the moment you give them a dynamic video, they kind of struggle with what the paper calls weak 4D perception. They just don't have that simultaneous grasp of space and time.
They can't track things properly.
Exactly, and that's the gap, that specific gap that 4D RGPT is designed to fill.
Okay, let's unpack this a bit. When we talk about 4D here, it's not just, a marketing buzzword. We're talking about the 3 spatial dimensions.
Length with depth.
Plus that 4th dimension of time, of motion.
Yeah.
And getting a model to understand that all at once is the whole game. So the model itself is 4D RGPT. It's a specialized multimodal LLM. But the real innovation, it seems, is how they actually taught it.
Yes, that's it. The core idea is this training framework they developed. Perceptual 4D distillation, or P4D for short.
P4D, okay.
And you can think of it like an intellectual transfer. Basically, they take all this very specific, very computationally heavy 4D knowledge from a huge frozen expert model.
Things like depth mapping, trajectory prediction, that kind of stuff.
Precisely. And P4D distills that knowledge into 4D RGPT, but not the massive, expensive computational engine behind it.
Wait, hold on a second.
Yeah.
I hear 4D distillation, and I immediately think there has to be a catch. I'm thinking this must be incredibly slow or add a huge computational spike.
That's the natural assumption, yeah.
Are we sure this isn't just adding another expensive layer that makes it impractical to deploy?
And that's the genius of it? No. This entire knowledge transfer happens without adding any additional inference cost.
So it's a free upgrade.
In terms of capability, yes, you get this massive boost in 4D understanding, but with zero hit to speed or efficiency when you actually run the model. That's the key engineering takeaway here. It makes it useful now.
That's actually incredible. But it brings up another problem. If you've built this amazing 4D engine, how do you even prove it works better if all the existing tests are like designed for 2D thinking?
Exactly.
We know the current 3D and 4D video benchmarks mostly focus on static scenes. They don't even have region-level prompting. So the authors realized they needed a better measuring stick, and they built one. It's called R4D Bench.
And this benchmark is laser-focused on depth-aware dynamic scenes. It specifically demands that the model understands things at a region level.
What does that mean in practice? Like, what's the difference?
Well, think of it this way. An old benchmark might ask, what generally happened in this video? R4D Bench allows you to ask something like, see that person in the red shirt? Track them. What was their exact distance from the parked blue truck at the 45-second mark? It demands that granular dynamic reasoning.
Wow, okay. That's a whole other level of detail.
It is. And to make sure the benchmark was solid, they used a hybrid pipeline, part automated, part human verified, to ensure the questions were high quality and, actually relevant.
So the million-dollar question, how did it do? What were the results?
The results are really compelling. On 6 of the existing non-region-based 3D and 4D benchmarks, 4D RGPT showed a really notable improvement, about a 5.3% gain on average.
A solid gain. But the real test, the one that validates the whole idea, has to be their own benchmark, the R4D Bench. How did it do there?
That's the one that matters. And on R4D Bench, it posted a 4.3% improvement over the baseline model.
Which doesn't sound as high, but on a much harder task.
A much, much harder task. And what's so fascinating is that this result validates their entire approach. It proves the model is effectively capturing explicit 4D signals. It's moving beyond just summarizing a video to actually performing spatial temporal reasoning.
So to wrap this up for you, what you've just heard is how these specialized models are making a critical leap. They're learning to see depth, movement, and context all at once, and without that speed penalty you'd normally expect. It's a much deeper understanding.
Right, and if a model like 4D RGPT can perceive dynamic regions this effectively, you have to think bigger. This isn't just about better YouTube captions, it raises a really important question for the future. What happens to the safety and reliability of autonomous systems like cars or robotics when their perception moves from just seeing in 3D to truly having 4D insight?
Welcome back to the Deep Dive. Today we're jumping right into a really fundamental challenge for the future of AI. We're talking about how to build sophisticated large language models that can function as reliable agents. And I don't mean simple chatbots, I mean AIs that can handle complex, multi-step, multi-turn tasks in messy, real-world environments. Our sources today point us toward a pretty major technical breakthrough, a new paper introducing something called Turn PPO. It's a method designed specifically to solve what might be the biggest bottleneck these agents face: long horizon reasoning. So let's unpack this. We know RL reinforcement learning is kind of the foundation for training these interactive agents, but the previous standard, well, it hit a serious wall.
It did. That wall was basically stability. For a while, the industry default was an algorithm called Group Relative Policy Optimization, or GRPO. And, it was popular because it let you do really speedy policy updates. But that speed came at a cost, a big one: long-term consistency. And that failure became brutally obvious in scenarios that required what you just mentioned, long horizon reasoning. Think of it this way. If a task needed a lot of steps, say planning a whole trip or writing code across multiple files like GRPO just like, well, it loses the plot. It really struggles to maintain its performance and stability over that whole extended sequence of actions.
So the key problem was GRPO's internal compass, basically. It couldn't stay on track. Yeah. Which begs the question, right, how does the AI even know if the last decision it made was actually good for the final goal way down the line? This brings us to a crucial piece of jargon: advantage estimation.
Exactly. Advantage estimation is the AI's internal feedback loop. It's how the agent decides, okay, was that last action a genuine step toward my objective, or was I just, lucky this time? And GRPO's way of estimating this advantage just wasn't stable enough over multiple turns. The agent would essentially forget what it was trying to do.
Okay, so with GRPO's limitations being so clear, did that immediately make proximal policy optimization, PPO, the obvious next step? Because we see PPO investigated as the alternative here, and the paper notes it was already found to be significantly more robust than GRPO, even before they started tweaking it.
Right, PPO was a great foundation. It was already a step up. but it still wasn't perfectly optimized for the unique challenges of these conversational turn-based agents. So to really boost that stability and effectiveness, they introduced the core innovation, Turn PPO, which is, like the name suggests, a special variant of PPO tailored specifically for multi-turn RL. The breakthrough is really in how it frames the problem. See, Turn PPO uses what's called a turn-level Markov decision process, or MDP formulation.
Turn-level MDP.
And that's the key distinction from the more commonly used token-level MDP.
So it's not looking at every single word or token the model generates.
Exactly. To visualize it, a token-level MDP is like trying to grade an essay by giving feedback on every single letter. It's just way too granular, too noisy. A turn-level MDP, on the other hand, is like grading based on complete sentences or even paragraphs. It groups the LLM's actions into a full logical turn before it calculates that advantage.
Ah.
And that structural change just radically stabilizes the whole learning process.
That grouping of actions.
Yeah.
That makes all the difference for reliable planning. And they didn't just stop at the theory, did they? They really put Turn PPO through the gauntlet. They used two pretty established benchmarks. The Web Shop Challenge, which mimics the complexity of real-world online shopping, and Sokoban, which is that classic puzzle that demands just pure, intricate planning.
And the results were definitive.
Turn PPO proved superior on both of them.
Yeah, and crucially, it maintained that superior performance even in tasks that didn't require that extreme long-term reasoning.
Right, which confirms that Turn PPO isn't just a niche fix for long tasks. It seems like it's a fundamentally better baseline for agent training overall.
Ultimately, yeah. The key insight is that Turn PPO provides a stable and reliable advantage estimation strategy that GRPO just lacked. It stops the LLM agent from getting sidetracked and losing its objective halfway through a complicated plan. It makes multi-step execution finally feel dependable.
Which leaves us with a provocative thought for you to consider. If Turn PPO or something like it successfully standardizes long-horizon reasoning, making it reliable, making it stable, how quickly will we see truly autonomous AI agents move from solving these simulated problems to tackling real-world complexities? Things like independently managing projects or autonomously navigating high-stakes physical environments. Something to chew on until next time.